So now for the second part of the lecture, I'm assuming that you actually worked through the problems, and what I wanted to do is to, once you've done this, is to actually start talking about them a little bit. Okay, the first problem says a 1-inch diameter garden hose will carry far more water than a 1/2-inch diameter water garden hose, everything else being equal. This phenomenon is explained by the fact that the wider hose has less surface area and therefore exerts less static friction on the passing water, has a higher Reynolds number and therefore introduces less turbulence into the flowing stream so it travels faster, has less inside surface area and therefore exerts less sliding friction force on the passing water. Now, or last, has more room for water to pass through and passes much of that passing water farther from the walls of the hose so that it can travel faster. And the idea with these is, again, this Poisson's law, is that the idea is that you lose energy by having the water close to the walls. The farther they get away from the walls, the less energy they lose, and that's why this varies much more dramatically than one would expect in terms of the flow rate. And so the only thing that really works is that the last one has more room for water to pass through and passes much of that passing water farther from the walls of the hose so that it can travel faster. It's just a matter that you lose less energy. Now the second one says, water flows through two tubes, one twice the diameter of the other. Both tubes have the same pressure differences between start and finish. The bigger tube will deliver water twice as quickly, 4 times as quickly, 8 times as quickly, 16 times as quickly. The cross-sectional area is 4 times as quickly. And so you might think that that would may make some sense. But again, remember that Poisson's law says that it varies as r to the 4th, which is basically r squared times r squared. So if you double r, then r squared is 4 times that, and so you have 4 times 4, so 16 times that. And so the correct answer is actually the last one, that you get 16 times as much flow just by doubling the diameter of the pipe. This has a huge effect in old houses. What I remember is I have this 100-year-old house, and they had galvanized steel pipes in it. In fact, they made it worse than that because they had the original galvanized steel pipe, and then also in the bathrooms they had copper pipe connected to it. And there's a sort of a electrolytic interaction between the copper and the galvanized steel. And so what happened is that over the period of years, the galvanized steel just closed down to almost nothing. So up on the second floor of the house, the flow of water in the bathroom was almost negligible. It was almost impossible to take a shower, at least when we first bought the house. So the first thing I did was I replaced the galvanized steel pipe. And when I took it out, these were like 3/4-inch galvanized steel pipe. The scale had built up so much, so there was only about 1/8 of an inch of free space, diameter going through that galvanized steel pipe. And replacing it with 1/2-inch copper pipe, all of a sudden I got huge amounts more pressure, more water going into the second floor. It's a gigantic effect. So just having slightly larger pipes makes it just a gigantic impact. And this has a even larger effect, say, for example, for arteriosclerosis, and this is why it's so dangerous. A healthy artery, basically, which is just, is completely open. If you have a pressure of 120 millimeters of mercury, the flow rate's basically 100 centimeters cubed. And so the idea is if you have arteriosclerosis, then you get sort of plating on the inside of the arteries, and it closes it down. And so if you basically have 120 millimeters of mercury pressure from your heart, then suddenly instead of you only getting 40% of the flow rate, which is why you tend really winded when you have arteriosclerosis. And so in order to actually maintain the same flow rate, the heart has to increase the pressure dramatically by almost a factor of 3. On the other hand, if you have 50% occlusion, then the flow rate is down only to 6% of what it was. And so in order to maintain the same flow rate, which you can't do, you'd have to go up over tourism, basically an order of magnitude factor of 20 in pressure. and your heart just can't provide that. 80% occlusion, you're just not getting anything at all. And so even a 19% decrease in the radius will basically halve the flow rate of blood through the artery. Now, the question is, well, why is it that water pours gently from an open hose? And the answer basically is viscous effects, because it wastes water's energy. The faster the flow rate through the hose, then the more dissipation that you have. And so when you're essentially, because of this loss of energy, and remember, water is incompressible, so you can't have part of the water running slower than the other part of the water, because otherwise the density would change. Since water is incompressible, the only way that it can change its internal energy is to lower the pressure. So the faster the flow rate through this hose, the more the energy loss, and so the pressure essentially drops as you go through the hose, so that by the time you get to the end of the hose, there's almost no pressure. So what is it that you're really doing? Well, when you cover most of the end, you slow the flow rate through the hose, which means that you have less energy loss. And so the pressure at the end point where your hand is suddenly increases. It's significantly higher. And so the water pours out of it at under very high pressure, and so you can spray it way up into the air. It essentially maintains almost all of its energy. So in other words, for very slow flow rates, Bernoulli's equations essentially work, and the faster that the flow rate is, the more dissipation that you have. Now, the other impact this has, and you can see it almost immediately, is that if you have basically an old building where you're taking a hot shower in the morning, and somebody comes into the bathroom and flushes the toilet, what everybody knows is that if you're in the shower, all of a sudden the water pressure, the water temperature skyrockets, and so you can just get really burned. The reason why this happens is that the toilet, when you flush it, it's connected up to the cold water. And so what happens is that when you flush the toilet, it has to refill the tank, and so all of a sudden the flow rate in the cold water pipes becomes larger. Because of the viscosity of the water, you lose energy, you lose more energy as it comes up through the pipes. And so what comes out of the shower head, suddenly you're at much lower pressures, and so the cold water rate going through the shower suddenly drops, and so then all you get is the hot water going through the pipes, which is why you burn yourself. So this is the impact that you've seen all the time. Okay, so I think this is a good place to stop. And so what you should do is now you should run through the second group of problems. Once you've done the second group of problems, then we'll start the third section of this